Hello everyone and welcome back to the channel CSAITTL. Today we are diving into the pointer choreography, advanced linear list architecture. If you're ready to master the engineering trade-offs in K-group reversal and palindrome detection, please remember to like, share and subscribe to the channel for more engineering insights. This intricate blueprint highlights the precise manipulation of pointers. On the left, we see a segment of a linked list with nodes like OX4A1C and OX5F2A connected by a segment length. On the right, we are introduced to a potential pending reversal path, indicating a transformation. At the center, a critical linkage appears to be compromised, marked by a radiation, illustrating a potential failure point. Our mission is to move beyond syntax to understand the soul of the machine, reconstructing the mechanical constraints of a sequential data flow, focusing on structural integrity during complex transformations. Our target specs involve manipulating next and prep pointers without losing the payload or breaking continuity. This detailed analysis is crucial for truly understanding advanced linked list operations. Let's first establish the physics of the system by comparing arrays and linked lists. On the left, an array is like a rigid block with numbered slots. It offers random access or teleportation, meaning you can instantly jump to any element by its index. The constraint is that arrays allow instant access. We can swap elements by index immediately. On the right, a linked list is a flexible chain, much like a train with connected cars. You can only move along the tracks, which means sequential negotiation only. The trade-off is that we gain structural flexibility, allowing for efficient insertion, but lose lookup speed. Every operation requires rewiring the couplings while the train is moving. There is no teleportation. You must travel the rails, emphasizing the sequential nature. Now, let's break down the atomic unit, the rotation, which is the fundamental step in reversing a linked list. The mechanism of reversal destroys the forward path to build the backward path. This is a delicate operation. The critical failure point occurs because once cur.next is redirected to prev, the connection to the rest of the list, which is from node to onward, is severed. If not handled correctly, you lose the rest of the list. The fix is to cache the future state or next before altering the present. This prevents data loss. The choreography for this rotation involves three steps. Number one, save next. This is the lifeline. Number two is redirect cur to prev. This is the rotation. Number three is shift prev and cur forward. This is the advance. This careful sequence maintains structural integrity. Next, we tackle a system stress test. The challenge here is not just reversing nodes locally within a group. It is about welding the new tail of group A to the new head of group B. As you can see here, we have architectural constraints, group boundaries. We need to accurately track exactly k nodes per group. Number two is connection handoff. After reversing a group, the original head of that group, now its tail, node 1, must eventually find the original head of the next group, which is node 6, to connect them. This is a critical connection failure, which you are mentioned here as welding required, if not handled correctly. Number 3 is incomplete groups. If the remaining nodes are less than k, the structure must remain untouched. The static break highlights the complexity of linking these reverse groups. To ensure stability, we implement layer 1 validation before execution. This adheres to the engineering rule: never start a demolition unless you can rebuild. Before altering any pointers, we perform a look ahead by scanning k nodes ahead using a telescopic probe or a sensor. The logic is straightforward. If count is less than k, abort reversal. This handles incomplete groups. If count equals k, proceed to rewiring. This validation ensures that we have sufficient resources to complete the reversal. The cost is that we visit nodes twice, once to count, once to reverse, meaning safety is greater than raw speed in this particular scenario. This upfront checks prevents critical failures. Next to layer 2, the internal reversal loop here. This is where the core work of reversing a group of k nodes happens. The process is to apply the standard atomic unit reversal exactly k times within the black box module. The interface for this module is crucial. It takes a start node and returns three critical references. Specifically, it returns the new head, node 3 in our k equals 3 example, the group tail, node 1, the original head, and the next group start, node 4, which is the head of the subsequent group. The straight transition is that the original head becomes the tail. This provides the crucial socket for the next connection in our larger linked list. Finally, we address layer 3, which is stabilizing the head and the dummy node. The problem is that the head of the list changes after the first reversal, 1 to 3, making standard logic fail if the root reference keeps moving. This hot zone at the beginning of the list requires spatial handling. The fixture is to use a dummy node. This temporary anchor provides a stable reference that allows us to treat the actual head of the list simply as just another node. The splice point shows where the new head of the reverse group connects, and the dummy node ensures a consistent entry point, simplifying the overall logic. Let's review the performance specification for reversing in groups. The time complexity ON. Despite having nested loops for probing and reversal, each node is processed a constant number of times, typically 2 times. This means the time taken scales linearly with the number of nodes n. The space complexity is O1. This is the gold standard because we use constant pointer regardless of list size, meaning no additional memory for a stack or auxiliary data structures. For optimization note, especially for massive K, pre-calculating the total length of the list can avoid redundant scanning n by k checks, further reducing the overheads. Now we move to the backward glance paradox and the palindrome detection. The challenge is clear. How do we verify symmetry or the palindrome when we cannot look backward? The array luxury allows us to easily compare add I with add n minus I minus 1 because of the random access. However, the linked list reality is a bit different. We must choose an architecture that allows for a backward comparison. This leaves us with two main choices. Number one, external memory or a stack. We copy data to an external structure to allow reverse access. Number two, structural modification. We physically alter the list itself to allow for comparison, then restore it. Let's explore design A, the external buffer. The mechanism here involves two steps. Push first half to stack, then pop, and compare with the second half. As you can see, elements from the first half of the list are pushed onto a stack. Then as we traverse the second half of the list, we pop elements from the stack and compare them. The pros are simple logic and it's non-destructive as the list structure remains untouched. However, the cons include a high memory footprint of ON. As the stack grows linearly with the list size, the verdict is that it's acceptable for the system with abundant memory, but suboptimal for embedded or strict constrained environments. Our second approach is design B, in-place structural modification. This technique allows for palindrome detection with O1 space. The technique involves 4 steps. Number 1, find middle of the linked list using the runner technique. Number 2 is reverse the second half in place. This physically alters the pointers in the latter half. Number 3 is compare pointers moving outward from the middle or in parallel to check for the symmetry. Number 4, restore the original structure by reversing the second half back. The efficiency is that it achieves O1 space complexity, making it highly memory efficient. However, the risk is that it requires modifying the data structure temporarily, which might not be suitable for all applications. To implement design B, the runner technique, fast and slow pointer, is essential. The application of this technique is for finding the midpoint of the fold as in the palindrome detection or detecting cycle as we discussed in our previous video. The logic is pretty simple. The fast pointer moves 2 steps for every 1 step of the slow pointer. Why? This eliminates the need for a separate length calculation pass. It provides dynamic measurements. in the one traversal, meaning you can find the midpoint or detect a cycle in a single pass without knowing the total length of the list beforehand. After in-place modification, system restoration and edge cases are critical. The leave no trace rule dictates in a shared memory environment, leaving a list reversed is polluting the environment. Therefore, you must restore the second half before returning the result. This ensures the list original state is preserved. Edge case handling is also vital. Empty single node lists are trivially a palindrome, requiring a minimal checks. Odd versus even length lists affect whether we skip the middle nodes during comparison, as the middle node of an odd length palindrome doesn't need a counterpart. These considerations ensures robustness. These are universal design patterns for linked list manipulation. These are reusable architectural components, not just tricks. Number one, the dummy node is an edge stabilizer to use when the head might change. Number two is runners. These are for cycles, midpoints, or looking ahead. Number three is split process merge. It is a strategy to break the problem down, like the Cray group layers. Solve locally, then reconnect. And number four is the three-pointer reversal. It is the atomic unit for reversing segments. These patterns are your toolkit for elegant and efficient linked list solutions. Ultimately, moving from mechanics to mastery. With linked list means more than just memorizing code. The key takeaway is this: true understanding isn't memorizing the code. It is the ability to close your eyes and visualize the state transition. When you can clearly see the prev, cur, and next pointers dancing in your mind, how they shift and reconnect, you own the machine. At that point, you aren't just a coder, you are a structural engineer of data, capable of designing and maintaining complex data flows with structural integrity 100%. This holistic view is the essence of mastery. Thank you for joining me on this deep dive. What are your favorite linked list patterns or toughest challenges? Share your thoughts in the comments below, and don't forget to like, share, and subscribe for more content that helps you master the mechanics of software engineering. Until next time, happy coding.